Our next example is a block on an inclined plane, which is just a board where one end is higher than the other. We're going to use a frictionless board now, but we'll see how to work with friction later. We're going to incline the board at an angle of theta degrees above the horizontal. We need a free body diagram, but we're also going to put in a coordinate system that's beneficial to us. We could certainly use the one where we have left, right, and up, down like we've used before, but there's an advantage to aligning the coordinate system with the plane itself, so that x goes along the plane and y is perpendicular to it. The advantage is here motion is in one dimension only in the x direction. With the other way, we'd have motion in y and x, and we could work with that, but this is easier. So we're going to use this tilted coordinate system. When we draw our free body diagram, we see that our forces are the normal force and mg, and we have to get components for mg. If we had done it the other way, we'd have to get components for the normal force, so there's not really any extra work with this method. But to get the components for mg, we realize mg is the hypotenuse of a triangle, and we want to find the sides that go along the y-axis and the x-axis. And to figure out how we'll do that, we need to figure out the angles of this triangle. The easy way to do that is to look at this picture, and we see, okay, we have theta here. We can imagine the triangle cuts off here. That would mean this angle is alpha. However, if that's the case, we can realize this is also a right angle with this green block, and this part inside the triangle must be 90 minus alpha, since this part out here we've already figured out was alpha. If this is 90 minus alpha is just theta, since we had a right triangle with right angle, theta, and alpha before. So we can replace this with theta. And what that means is we can now find the x and y components pretty easily. mg times the sine of theta will be the opposite side. That's mg, x component. And mg times the cosine of theta will be the adjacent side, which is the y component of mg. This means we can go back to Newton's second law, where we have some of the forces in the x direction is max, and some of the forces in the y direction is may. And we do the y component first. The force we have is normal force, and then mg cosine theta. And the sum of those, and the mg cosine theta is negative since it points down, is equal to may. But this is the other advantage of working with the coordinate system we've chosen. We know ay has to be 0, because otherwise the block has to jump off the plane or dig into the plane, and we know that doesn't happen in real life. So n minus mg cosine theta is 0. That tells us the normal force is mg cosine theta. This is actually not a particularly useful result right now because we don't have friction. We are going to need it later when we use friction. One interesting thing here is scales like your bathroom scale or a scale in the chemistry lab. What they really measure is normal force, not weight. They figure out the weight because they assume the normal force is equal to mg, but that's only true if the ground is flat. This is why if you have a slightly fancier scale, there might be a bubble level on it to show you that you are level before you start measuring and start getting the wrong answer. The x direction is a little bit more interesting for what we're doing in this case, and the only thing we have is the x component of the weight, and that points down the plane. So we have mg sine theta equals max. We cancel the masses and we get the acceleration along the plane is g sine theta. And we can look at the limits of this and check and see if this agrees with reality. If the plane is flat, theta is 0, and we get 0 acceleration, which makes sense because we don't expect the block to move on flat ground. If the plane is vertical, we raise it all the way up so theta is 90, we get that acceleration is g because that's just free fall. Now that we have this acceleration, we could answer a bunch of kinematics questions about the problem. For example, if theta is 30, how fast is the block going after sliding 3.5 meters? We know the acceleration is g times sine of 30, and we can use one of the kinematic equations, putting in our new value for g, 4.9, our new value for acceleration, which is g sine theta, 4.9 meters per second squared. We solve for the velocity and get 5.86 meters per second. Really, any kinematics problem that you were asked in the first part of the course can now be redone on an inclined plane with this effectively slightly different acceleration. One thing that is hard for people to understand. If, for example, you might get a question like if we take this block and throw it up the inclined plane at some velocity, then we want to know how far it goes, how long it takes to stop, that kind of thing. But the thing you have to remember is that the initial velocity and position are in no way related to the acceleration. It's a completely separate problem. And it's very common for students, if they hear about a problem like that, to want to put a velocity vector somewhere in here. But this vector diagram, this free body diagram, is for forces only. Velocity is an initial condition, and we don't care about that until we've already solved the F equals ma problem. Okay, another problem. What if we have a block on a frictionless table attached to another block by a massless rope, and we've got a massless frictionless pendulum connecting them? We look at the free body diagram. We see that mass m1 has a normal force and gravity, but also it's being pulled by the rope, and we represent this by T for tension. Tension always moves away from the object you're interested in, because you can't push with something like a rope, you can only pull. The other mass, m2, the only forces acting on it are m2g, gravity, and a tension pulling upward. There is no normal force because it's not sitting on anything. The two tensions are going to be equal because this pulley is massless. Closer to the end of the course, we'll use regular realistic pulleys that have mass, and we'll see we'll have to call this tension T1 and this one T2, and they won't be equal. Since we have two masses, we have two sets of Newton's second law equations. So we've got mass 1 in the x direction, mass 1 in the y direction, mass 2 in the x, and mass 2 in the y. Now there are no x forces acting on m2, so we can get rid of that one. For m1, we can start with the y forces. We have n minus m1g is m1a1y. But again, we know there will be no acceleration in the y direction because the block m1 is sitting on a table. It won't jump up and it won't dig down, so it has to be 0. So we get n equals mg. This is true, but again, it's not particularly useful until we get to friction. In the x direction, the only force we have acting on m1 is T. So T equals m1a1x. For m2, all we have are forces in the y direction. We list them. We've got T pulling up and m2g pulling down, and they have to equal m2a2y. The problem here is we have two useful equations, this one and this one, but three unknowns because we don't know T, a1x, or a2y. We can't solve this unless we can think of another equation. And what that would be, we notice that a1x and a2y have to have the same magnitude. They have to be accelerating at the same rate or the rope will break. The signs don't have to be the same. As the block m1 moves to the right, a1x will be positive, but m2 will fall, and that means a2y will be negative. So, since we have this relationship between the accelerations, we could just define one acceleration a and say it's equal to a1x or negative a2y. We rewrite our equations. T equals m1a1x is now just T equals m1a, and T minus m2g equals m2a2y. We get T minus m2g equals negative m2a, because again, a2y is negative a. We rearrange this last one, we get T is m2g minus m2a. Now we have two different equations for T, but if the tensions are the same, these equations have to equal each other. So we could say m1a from the first equation equals m2g minus m2a from the second. We could rearrange that and get that acceleration is m2g over the total mass. If we look at the limits, if m1 is very, very large and m2 is small, we'll only get a tiny acceleration. Now, in the real world where we had friction, we probably won't get any acceleration in that case, but remember, we don't have friction yet. On the other hand, if m2 is huge and m1 is small, we still have the limit that this m2 will not fall faster than g no matter what we do with m1. It'll always be slower, even if it's just a little bit slower.